Well, hi again, Tim here. And today, lecture number 10 is on Fermi gases and white dwarf stars. So we'll just review a bit from the last lecture, which is the equation of state and pressure of an ideal Fermi gas. And then we'll move on to talk about white dwarfs. So up till now, we've been taking as our example of an ideal Fermi gas electrons in a metal. And for this lecture, we'll consider another system where we have a Fermi gas of electrons, and this occurs in the cores of stars, dying stars, essentially. And what we'll do is we'll examine this, and we'll actually find some interesting results about the stability of white dwarf stars. So in the last lecture, we found the equation of state for an ideal Fermi gas, and we started with this equation that the grand potential equals minus PV, and then using the expression we derived for the log of the grand sum, which gives us the grand potential, we found that the equation of state basically that PV is 2/3 U over V. And then if we plug in the result for the mean energy, we found in terms of the Fermi energy, we have that the pressure is 2/5 the number density times the Fermi energy. And remember, we showed that for an electron gas in a metal, this pressure was something like a couple of atmospheres. So now let's look at another example of an ideal Fermi gas, which are white dwarf stars. Okay, so white dwarf stars basically have very high pressure. We'll see it's about 10 to the 17 atmospheres. So, and this pressure is due to the electron gas, much as we described before. Instead of 2 atmospheres, though, we'll find that it's something like 10 to the 17 or greater. So how does that work? Well, a typical star like our sun, normally it has a hot core. When it's undergoing fusion, then the temperature is something like 10 to the 7 kelvins. That corresponds to an energy, kBT, of about 900 electron volts. And this heat energy, of course, comes from thermonuclear reactions. So it's very hot. Of course, this energy scale is much higher than the energy of the binding energy of electrons to atoms. So atoms are completely ionized, and they create this huge high temperature electron ion plasma. That's when a star in its kind of living state while it's still undergoing fusion. So in young stars then, like our sun, the electron pressure is sufficient to withstand the weight of the material pressing on the center, that is, the gravitational forces that want to collapse this are balanced by this electron ion plasma, this pressure, and it prevents collapse. But in old stars, the hydrogen at the core of the star has run out and fusion stops, and then what happens is the core cools and starts to shrink. But as it does this, of course, gravitational potential energy gets converted into kinetic energy of electrons, and this slows the cooling process for a while. But eventually it cools, and in white dwarfs, as we'll see, the collapse beyond a certain point is prevented by this ideal electron gas, the pressure from this ideal electron gas. And we'll see that that's actually at a relatively low temperature, what we mean low temperature compared to the Fermi energy, so the Fermi temperature. So white dwarfs typically have the mass of the sun, but the radius of the Earth. And one example is Sirius B, and it has a mass of about 2 times 10 to the 30 kilograms, and a radius that's about 5.6 times 10 to the 6 meters, and a volume, of course, that's listed here. And so with these parameters, we can find the pressure, and for now we'll assume that the temperature is less than the Fermi temperature. We'll find the pressure, and we'll see what we get. So let's first find. So here's the pressure, but to get the pressure, we need the Fermi energy, or equivalently the Fermi temperature. So let's find what we would get, and we'll assume it's an ideal Fermi gas, and then we'll see what its we'll see what we need. Then that will tell us if this temperature, if we're really in this limit, we can use the ideal Fermi gas at 0 temperature. So we'll find the Fermi temperature and we'll compare it. Well, let's just compare it. To be safe, we'll compare it to the temperature in a burning star, even though the white dwarf will be cooler than that. So we'll be safe if the Fermi temperature is much. We'll be safe to use the ideal Fermi gas at 0 temperature if the Fermi temperature we find is greater than this by a couple order of magnitude. Oh, by the way, here is a picture of a white dwarf. It's known as Sirius B, and this picture was taken by the Hubble telescope. Obviously, this is Sirius A, and this is Sirius B. This little tiny point of light here. For those of you who are familiar with the sky, Sirius is a constellation. You can see in the sky here. You can see it in the northern hemisphere. You can see it in the southern hemisphere, although it seems to be upside down here from my point of view. But it has a very, very bright star. It's actually the constellation is known as Canis Major, the big dog, and it has a very bright star that's usually called Sirius, and this is the one you usually see when you look up in the sky. But with the Hubble telescope, you can see its partner, this little white dwarf here. And this was taken by the Hubble Space Telescope. If there's any astronomers taking the class, or people, or even amateur astronomers, people that have their own telescopes, they can probably tell me what this cross thing here is. It's actually an artifact. I have a telescope as well, and it does the same thing. And amateur astronomers in the class will know it's basically, this comes from the support in a Newtonian reflector telescope. You have a sort of the light comes in and bounces off a primary mirror and then goes back up and reflects off the secondary mirror, and the secondary mirror is usually held by a little cross brace, a little cross thing here, and you get this artifact then from. So you can tell from this. Obviously, the Hubble Space Telescope is something like a Newtonian reflector. It's probably a Schmidt-Cassegrain or something. But anyway, that's just for those who might know some astronomy or some telescope or have a telescope. Anyway, whatever. That's it, and it's small. And so let's think about our white dwarf and how it actually can be considered as an electron gas, and an ideal electron gas, an ideal Fermi gas, that is. So, what are white dwarfs again? We'll assume that the nuclear fusion has ceased, and all the hydrogen's been converted to helium. So, all we have left then is helium, and that's not completely true. Actually, larger stars fuse helium to carbon and oxygen in this red giant stage. So another star you might see in the sky, it's been in the news a lot, is the Betelgeuse, which is in the constellation Orion. And you can tell by looking at its red, and there's been a lot of that in the news recently because its luminosity seems to be low. But anyway, we'll see. It doesn't matter. We'll get the similar answer, whether we assume it's helium or carbon and oxygen. We'll see how that works here. The point is that we need to calculate the number of nucleons in the star, and then we need to figure out how many, based on the mass of the star and the number of nucleons, we can figure out the density of our electron gas. Because remember, the Fermi energy depends upon the number density of electrons right. So that's what we need to find. So let's start with the number of nucleons. Well, that's just the total mass divided by the mass of a nucleon. And so if we take that parameter for Sirius B, for the total mass here, and we divide by the mass of a nucleon, we'll find that there's, a very large number of nucleons. And if we're assuming helium atoms, we know each helium atom contains 4 nucleons, that is 2 protons, 2 neutrons, and each helium contributes 2 electrons to the electron gas, right? Each helium atom. So basically, for 4 nucleons gives us 2 electrons, basically. And this is the same for carbon and oxygen. So we get the same thing if we assumed this kind of white dwarf. That is, the number of electrons is always half the number of nucleons, right? Because this is the, for all these, for helium, for carbon and oxygen, which is here. So that means the number of electrons is half this number, basically. Well, if we know what the mass of the electron is, and now we can just substitute, this is the formula we found for the Fermi energy of an ideal Fermi gas at 0 temperature. That's the Fermi, well, the Fermi energy is defined at 0 temperature. That's the Fermi energy, and we want to put some numbers to it. You'll find we get something like 0.33 mega electron volts, right? So that's pretty large Fermi energy, right? And if we convert this to a temperature, that is by dividing by Boltzmann constant, remember, so about 100 microelectron volts equals 1 Kelvin. It's actually 86.2 microelectron volts equal 1 Kelvin. I know that because I used that relation so many times in my own work. Then you can find that this corresponds to, means a Fermi temperature is something like 4 times 10 to the 9th Kelvin, which is very large, right? So even if we assume the temperature is 10 to the 7 Kelvin, that applies to a star that's still burning, we still have the temperature much, much less than the Fermi temperature here. In fact, the white dwarf is colder than this. So even if we take this temperature, you see, remember the correction terms. If we use that Sommerfeld expansion and we take the first terms in the expansion for non-zero temperature, they're always proportional to T over T Fermi squared. So even here, that's like 10 to the minus 4. And even for a white dwarf, it's going to be quite a bit less than this. So the point is that the 0 temperature result is very accurate, and so we can use the ideal Fermi gas at 0 temperature to understand what's happening, even in a white dwarf star. It sounds a bit funny because we're talking about a star that's obviously very hot or has been very hot, but the point is, because of the very, very large density here, it's a very, very large Fermi temperature, right? So I plugged the volume, but you can do this. I plugged the volume in from basically the radius. Let's see, where did I have that? Oh, well, I didn't write it down, but of course I used the volume from the radius, the observationally determined radius here. Yeah. Which is, like the radius of the Earth or something. Okay. So, very large Fermi temperature. And using this, remember, we just plug that into our equation, the state, and we get the pressure. And you can see that this corresponds to, as we said, something like 2 times 10 to the 17th atmospheres, which is a very large pressure. So now we'd like to see under what conditions this pressure is sufficient to prevent the further collapse of the star. That is, so what happens is the star runs out of fuel, and then because of gravitational forces, it starts shrinking and shrinking, and then at some point, and the Fermi pressure gets higher and higher. So at some point, that pressure, we want to see if that pressure is enough to prevent further collapse of this white dwarf star. So basically, a white dwarf is stable when the total energy, which consists of this electronic energy, that is energy of the ideal Fermi gas, plus the gravitational energy, when there's a minimum in this. A minimum as a function of radius. So what we need to do is we need to express both of these as functions of r. We're used to that for this term, of course, but we're going to express both of these as a function of the radius r, and then we'll find the minimum by setting du dr equal to 0, and we'll find the value of r for which this is minimum. And if there is a minimum, then the white dwarf should be stable. And because we just showed that the temperature is much, much less than the Fermi temperature, we can just take the 0 temperature value for the ideal Fermi gas, for the energy of the ideal Fermi gas. It's 3/2 N times the Fermi energy. And we can plug in the formula for the Fermi energy we derived earlier, and we get, so we get this value. And if we substitute, we want it, of course, in terms of radius, and we just use, so we'll assume that the star is just a solid sphere, and of course the volume is 4/3 pi r cubed. And so now, and if we plug that in, then we can find that basically the electronic energy, that is the energy of the ideal Fermi gas, so this star, is like some constant A over r squared. It goes like 1 over r squared. And just by substituting in, you'll see that we have this value of the constant A. Right. Okay. Well, we know from classical mechanics what the gravitational potential is. It's just the energy, it's the work done to assemble this solid sphere of mass, and we'll just assume a uniform sphere of mass m and radius r, and you can calculate that the gravitational potential energy has this form. It's minus b over r, and this constant b is 3/5 gm squared. That's just, you probably did this in first year physics, first course in mechanics. So now we have the electronic energy and we have the gravitational energy, and we'll just write them. What we're really interested in is the dependence upon radius r. So let's just write it this way. We can always plug in the constants a and b when we need to, and say we minimize this by taking its derivative with respect to the radius r. We get this equation, and we can solve this for r0, and it's just that the minimum occurs at r0 is 2a over b, and then we could plug in the a and b if we want. So we'll call this minimum r0. And you can convince yourself it's a minimum by looking at the second derivative, or you could actually plot this and see, but it is a minimum rather than a maximum. Yeah, so we put in the values in a and b for cirrus b, and we find that the r0 is 7 times 10 to the 6 meters. And that's actually really good, because that's close to the observational value. The observational value was 5. So let's see, I can't remember. Let me go back. Let's go back and see what the observational value was. Yeah, 6 times 10 to the 6. And we get 7 times 10 to the 6. So that's really good. That tells us, we're probably correct that this white dwarf Cirrus B has contracted down to its stable minimum, and and that's what a white dwarf star is. So good. There's some success. We should be happy with that. And we also note that on the basis of this calculation, there's always a minimum U at some R0. So according to this calculation, white dwarfs should always be stable, right? There's always, independent of the mass or any parameter here, there's always a stable minimum, right? And that's because these have different dependencies on R. But anyway, it's always a stable. That's what we would conclude. Should always be stable. But there's one little thing we left out. Well, one little thing, one big thing we kind of swept under the rug. And that is, in studying the properties of this particular ideal Fermi gas, we used our results from before, and our results from before meant that we used a non-relativistic energy momentum relation, that is, that the energy is p squared over 2m. That's non-relativistic. And, we just saw that the Fermi energy is really, really huge in this white dwarf. So we really need to ask ourselves, hey, is this a reasonable assumption, right? So to do this, we should really calculate what's known as the Fermi velocity, v sub f, and compare it to the speed of light. So, and that's easy to do. Well, the Fermi velocity is just defined as if you set the Fermi energy equal to sort of the kinetic energy, 1/2 mv squared. You call that the Fermi energy. We're solving for the we'll call this the Fermi velocity. And solving for the Fermi velocity, of course, we get this. And if we plug in the numbers we found for the Fermi energy and the mass electron, we'll find, lo and behold, that the Fermi energy would calculate is like something like 3.4 times 10 to the 8th meters per second. And if you look at that, you'll say, wait a minute, that's greater than the speed of light. So maybe we're in trouble here. And maybe we better use a relativistic energy momentum relation. Basically, the energy epsilon is this square root of m squared c to the 4th plus p squared c squared minus the rest mass energy mc squared. All right? That's a relativistic energy momentum relation. Okay, so now we've got to do that, and well, that's actually we'll do this in detail. But first, let's try to, we might want to see what we can work out by making another assumption, and that assumption is when we solve for when we get such a large velocity from this estimate, which is, over the speed of light, which we know is not possible actually because you can't exceed the speed of light. Well, maybe we should assume that we're in the ultra-relativistic limit anyway. And that turns out to be a bit easier than doing this full calculation. We'll do the full calculation, but let's see what we get from assuming we're really very relativistic. That is, we'll do that. But in either case, we have this different energy momentum relation. Remember, we derive the density of states for ideal Fermi gas based upon this relation. That is, we quantized our fermions in a box, and we found allowed wave vectors, and we had the density of states in wave vector, and then we converted it to energy by using this relation. If you remember, if you go back and look at that, if we have a different energy momentum relation, then we have to, have another look at our density of states and energy and rederive that. So that's what we have to do before we can go any further. But in our first approach of this, we'll assume we're in the ultra-relativistic limit. And what is that? Well, in the ultra-relativistic limit, we assume that this term, Pc, is much, much greater than the rest mass energy squared. That is, this particle is moving fast, and so it basically means in this equation we can forget about the rest mass energy, or we can expand this. We can just approximate this, and if this term dominates, we just get so basically E equals Cp or Pc, which is, and then if we convert to wave vector, it's just P is h bar k. And we have this simple relation. Okay, well, we'll see next week that this is the same kind of energy momentum relation one finds for photons, which is not surprising actually. Because basically you're assuming that you're ignoring the rest mass energy, and photons have no mass. It also applies to phonons. We'll see that. So we'll see this next week when we talk about radiation in a cavity and phonons in a solid. But we'll just do that here as well. So ultra-relativistic limit will do this. Now, the point is we can still use particle in a box results because we're still solving the Schrodinger equation. We're still quantizing things in a box, so we can use those energy levels. So those wave vectors, the allowed wave vectors. Remember, that's how we started out when we got the density of states and energy. We started from the density of states and wave vector, and if you can go back and look at that, this is by counting the number of states, in a small shell, spherical shell, and wave vector. We found this formula for density of states in wave vector. Right? Go back and look at that. So we can still use this. It's just we have to use a different. When we transform to energy, we have to use this relation. That is, we do the usual thing. In this case, it's very simple because this the energy momentum relation here, it's just a constant out front. It's just a constant. So of course we're going to get epsilon squared just like we have k squared here. It's just a couple of constants that come into this derivative, and we get this value for the density of states and energy. So instead of going like energy to the 1/2 power, that is square root of energy, it goes like energy squared, just like the density of states in wave vector. That's because this is a linear. Again, it's because this is a linear relation. Okay. So now we want to calculate the density of states, we want to calculate the mean energy like we did in the non-relativistic case. But first, of course, we have to find the Fermi energy before we do that. And if you remember how we did that, we looked at the constraint of number of particles, right? And at zero temperature, we only have to integrate up to the Fermi energy, where this, remember, the Fermi-Dirac distribution is 1, and then it chops off, goes to 0 at the Fermi energies. So we use this constraint again, and then we can solve the Fermi energy in terms of these parameters. Let's see, right? And of course, I put in a factor of 2. I've again for spin and going from here to here. So from now on, I'll talk about the density of states. It'll be this multiplied by 2. So we can just redefine our density of states by multiplying by 2, and we'll consider 2 spin states. Well, anyway, we do this integral, which is quite easy, and of course we see what we get, and we can solve then for the Fermi energy, and now we get a different expression than we had before. This expression, of course, involves the speed of light. Okay, so now the trick we're going to use again is the one we've done before. We could work everything out with this density of states times 2, but of course, as I showed several times before, it's a lot easier to do other calculations if we write the density of states in terms of the Fermi energy. And to do that, we just assume, of course you can see it's not assuming, we see the density of states. The way to do this trick is you say, well, density of states is some constant times epsilon squared, and then I'll find the constant. And you could do that by a lot of algebra, but the easiest way is just to do this and find the constant here. So I can write the density of states as 3n over Fermi energy cubed times epsilon squared. And that'll make the calculations a lot easier for the rest of the things we do. That's the same old trick we had before. Okay, so let's do that now. We find the electronic energy. This A is a constant. This A is this constant, by the way, which we'll plug in soon. And there we go. We find that the energy. So what did we find before? 3/5. It's actually 3/4 n times the Fermi energy. And if we plug in the Fermi energy we found back there, we can evaluate this in terms of the volume or the radius and the number of electrons. So let's just summarize this then. Remember, for non-relativistic fermions, we found this relation for mean energy, that is 3/5 total number of electrons times the Fermi energy. And the Fermi energy of this form. And for this ultra-relativistic regime, we find 3/4 n times the Fermi energy. But the main thing is the dependence here on the number is different. So if I multiply the number dependence here times the number dependence in there, I get a non-relativistic, I get n to the 5/3, whereas it's n to the 4/3 in the ultra-relativistic limit. And also the volume has a different dependence. If we plug in the volume in both these equations, well, let's plug it again. We'll plug it again. We did this in the non-relativistic calculation. Let's do it now. And what we find now is that the electronic energy, that is the kinetic energy, is A over R. So it goes like 1 over R instead of 1 over R squared. And we can find the constant A here. And that's the same as the R dependence on gravity, which is, before minus B over R, with B equal to this 3/5 big G times M squared. And so, obviously this is quite different. And, if we add these two terms together, the potential energy is going to be changed drastically when A equals B. So, you might think that depending on A and B, the potential energy is going to always go like 1 over R. But if A minus B is positive, then it's going to go like positive 1 over R. And if it's negative, it'll go like negative 1 over R. You might worry that if A is larger than B, this might suggest that there's no stable minimum at all, because 1 over R doesn't have a minimum. But that's actually, we'll see, that's just because we took this ultra-relativistic approximation. And when we do this in detail, we say we don't really have to worry about it. But what we do have to worry about is when the sum of these become negative. And that's sort of, and you can see that will always happen at some point depending upon the mass. Well, it will happen depending on the mass, right? So we plug in the values for A and B. Well, we don't have to plug them in. Let's just look at it. A goes like m to the 4/3, and B goes like m squared. So if I start increasing the mass, then what's going to happen? So at some point, m squared becomes bigger than m to the 4/3 power. So for small m, it starts out that this term's bigger. But as you can show this by plotting it. But at some point, this m squared term will get larger, and so for large enough, B is going to be bigger than A, and the total energy will become like minus 1 over R. And so that happens when A equals B, of course. And if we set A equal to B and solve for the mass when that happens, we'll get this critical mass. And if we plug in the numbers, then we find that that's about, well, it's just in kilograms, but it's better to put it in units of, this symbol means solar masses. So for, just under about 2 solar masses, 1.72 solar masses, then our calculation shows that the white dwarf, the minimum of the energy is at 0 radius, right, essentially. And we'll see that happens in the general, when we actually do the full relativistic energy momentum relation. But that's what we get. And so what happens then, of course, and we won't discuss about beyond this, but then when this becomes unstable, then what is found is that the core of the white dwarf collapses, and it collapses and becomes what's called the neutron star. And so basically all the nucleons, instead of having a bunch of helium atoms around with their electrons, basically the helium atoms start clumping together and become, and you have some reaction. Well, actually what happens is there's a supernova, right? First of all, under this collapse, this is what's responsible for a supernova, and then sometimes what's left is a neutron star. So what we predicted is that stars that are large enough and become white dwarfs that are large enough, they're not stable, and they collapse. And when this happens, it's actually quite an amazing event. It's called a supernova. Actually, there's different kinds of supernovas. There's type 1 and type 2, and this is a classic supernova then. But we're not going to discuss what happens after this point. We just wanted to point out the stability here. Now, at this point, we're going to move and we're going to actually do the calculation using the full energy momentum relation. So if you want, take a little pause, review where we got to up to now. I'm going to take a little pause myself and have a cup of tea. And so if you do that and come back in a few minutes, we'll do the calculation for full energy momentum relation. And this is not actually on the syllabus, so I mean you won't be responsible for this part, but I want you to see how it works, just in case you're interested, or you might want. It's kind of a classic result, and of course it's going to be much more difficult than we've done before. So once again, you won't be responsible for knowing this derivation. I just want you to see it for your own sort of personal education and understanding. But don't worry about it, this piece for assignments or the exam. Okay? All right, we'll see you in a few minutes. Okay, well, I'm back, and I hope you had a small break there. And so now I'm going to do we're going to look at the stability of white dwarf with the general treatment. Now, like I said, this is not on your syllabus. You don't have to know it. You're not responsible for it. I just want to give it to you to show you an example. Of course, when we do something using this full energy momentum relation, it's going to be a bit more difficult than what we've done before. And I'll show you the point of me going through this is almost to show you how some strategies for solving something that's a little bit more difficult than you normally get. So this is just for fun for you who are interested. Anyway, we have the full energy momentum relation for relativistic electrons, and of course we've seen it before. It looks like this. And now we're going to calculate mean energy and so forth, and it turns out that it will be easier to integrate over a wave vector instead of energy. Usually we calculate the energy by integrating over the density of states in energy, that's G of epsilon, but for this problem it's easier to work in K, and we can do that, and it'll become clear why that is. So we'll do what we usually do, where we find, usually we'd find the Fermi energy by this similar equation, and now since we're integrating over a wave vector, we'll find the Fermi wave vector, Kf, and of course we could always get the Fermi energy because we know this relation between K and epsilon. So it turns out this is easier, and we already have the density of states in wave vector anyway. It's like this, and if we do this, we'll find that the Fermi wave vector is exactly what we found before in the ultra-relativistic calculation. It's just the energy momentum relation is different. But if we do go to the relativistic limit, we'll see we get the same answer, which tells us we're on the right track. The point is this: in the wave vector point of view, nothing's really changed. It's just this relation, and of course that will come into when we calculate the energy, of course. So, but let's do the same trick we usually do with G of epsilon. Instead of writing f of epsilon as this, we'll write the density of states in wave vector in terms of the Fermi wave vector, same trick we did before, by assuming it's constant times k squared, and we find the constant, and then we have this. And then we can use this now in determining our energy. So now the energy is a similar calculation, except we're doing it in wave vector space. We're integrating over the density of states in wave vector up to the Fermi wave vector because we're at zero temperature, and we multiply by epsilon to find the mean energy. And here's where the the general energy momentum relation comes into, right? So now we've expressed epsilon as a function of wave vector. But now we're doing this calculation by an integral over wave vector. We could have done that at any time before, doesn't matter, but it's very useful here. And so we get this integral, and if we separate these two pieces, we can complete this integral of this term because it doesn't depend, it's only k squared, of course, so we know how to do that. Okay, so we look at this, and we say, well, there's a lot of constants running around, and it will really simplify things a lot if we kind of find dimensionless variables to make this look a bit simpler. And it might seem like a thing we do just to help with the calculation, but we'll see the process of doing this will identify a relevant energy and wave vector scales that will actually have some physical meaning in addition to help us with the calculation. So the first thing we do is we see this term here, which is, of course, you recognize as the number of electrons times the rest mass energy of an electron, MEC squared. And so let's just let's divide the energy by this energy scale. Both terms here, of course, when I divide this by this, I get 1. And inside the integral here, I divide out the n. And if I move this inside the square root there, I get 1 and this term here. And so that's considerably simple. But then we look at our wave vector, and we realize that this is momentum squared, and this is units of momentum squared. So let's define a new variable x, which is a scaled wave vector that is basically h bar k divided by MEC. And when you do that, I mean, we don't, at this point we could just use that, but if you remember physics from your quantum physics, you'll recognize this, that if I do that, basically my x is just k over pi 2 times the Compton wavelength. And if you remember, the Compton wavelength is given by h over MEC. So we've actually identified that this scaled wave vector is apart from 2 pi, it's really measuring wave vector in units of the Compton wavelength of the electron, right? So let's then turn this integral instead of over k into the x. So we have scaled energy, and now we have scaled wave vector, which is to a factor of 2 pi as in units of the Compton wavelength. And so now we can write down the scaled energy here, and I've just put the steps here explicitly. I'm going to convert this to an integral over x. And so, I do that at this point, and I have the integral in x, but I have to change the limit of integration basically to x0, which is related to the Fermi wavelength in this manner, of course. And now we see the integral for the scaled energy is quite simple. We have it over this dimensionless x minus 1, and the limit of integration is given by this scaled Fermi wave vector. We'll call it x0. And in principle, that's all we have to do is evaluate this. Now we look at this x0. Here it's the scaled Fermi wave vector. Wave vector is like an inverse distance, and so if we put in actually what the Fermi wave vector is, we can evaluate this x0 either in terms of density, number density, or assuming the usual expression for the volume, we can put this in terms of the radius, of course, the radius of the white dwarf. And that's what we would get for x0. So that's just our scaled Fermi wave vector in units which we want to find stability of the radius. Well, it's like radius, it's 1 over radius, the dependence, of course. Right? Okay. So, like I said, we can think of x0 as an inverse dimensionless radius if we want. Let's call that little r. And you'll see that it's just the radius scaled by this r0, where r0 is this expression. In fact, if you actually look at this enough and think about the Compton wavelength, you'll find that this r0, this sort of natural unit of distance or radius for this problem, is the radius when the Fermi wave vector divided by 2 pi is the inverse Compton wavelength. So that's a really natural sort of radius, r0. It's small too, but anyway. So let's put that all together. We have finally the scaled energy of our ideal Fermi gas in terms of this variable x, and in this scaled 1 over the scaled radius, which is related to the Fermi wave vector. And so, and of course, now that we have the electronic energy in this scaled form, we need to do that with the gravitational part as well, and we need to put it in the same variables, and that's just some algebra that I'm going to skip right through. You can go through it, and in the end we find, of course, the gravitational potential energy still goes like 1 over r, but it's like this m. Well, here's another thing. We get the potential energy here, the gravitational potential energy. Let's just go back. I went a bit too fast, and I've got this form, and it goes like the mass of the white dwarf to the 2/3 power. We have the mass of the nucleon. So we'll also have a scaled mass then, where we'll use the critical value we had before, basically, that we found in the ultra-relativistic treatment, and we'll use scaled mass. Because, of course, the gravitational potential energy is going to depend on mass, and like we did with the other variables, we need to write that in some sort of scaled value. And we'll use like I said, we'll use the critical mass we found from the simpler ultra-relativistic limit. And in the end then, and we'll call that little m, we find this really simple form now for the gravitational potential energy. So now, it took quite a bit of work, but you can see this is a lot less daunting, and we're working in variables that are kind of natural to the problem. So this is a kind of a general technique you use in a lot of areas of physics when you have to do rather complicated calculations, and so that's part of why I wanted to show it to you. But anyway, now we have this, and actually we can actually do this integral. This integral can be done, and here's what you get, and we add here. So here's the electronic energy and the gravitational potential energy, and still that is actually quite complicated. Now you could solve this graphically, and I'll do that. I'll show you graphically on the next. And you can see if the mass is above some critical mass, we don't know what it is at the moment, but that will correspond to this scaled radius of our white dwarf going to 0, because there's no non-zero stable point, right? That's what we said before. So if we do that in this equation, we can see right away that if you let r go to 0, you'll find that the critical value does occur when this equals 1, basically. So, but let me show you graphically on the next page, and I'll come back to this. So let's just look at this. So what I've done here is I've plotted that scaled total energy for different values of this scaled mass. Remember, mass is total mass divided by this critical mass we found for the ultra-relativistic problem. And here's what you get, actually. And you can see exactly what's happening. Here's the blue curve is when the mass is just below the critical mass, and the yellow is when mass is greater than the critical mass, and right at 1, of course, it has this. So it's becoming unstable. So the interesting thing is we found the same critical mass as before in the ultra-relativistic limit, but unlike in the ultra-relativistic limit, we do see there is a stable minimum here when mass is below the critical mass. And so we didn't, there's that little point of confusion in the ultra-relativistic limit that the total potential went like 1 over r, and so it wasn't clear that there was a stable mass for below the critical mass. It wasn't clear how that worked, but so now it's quite cleared up. And so just some historical notes on this calculation I went through. This calculation was actually done by a guy called E.C. Stoner. You probably recognize his name from magnetism and other things, and he did this in 1929. And he assumed just what we assumed, which was a uniform star density, which isn't quite realistic, but the whole concept of combining relativity with Fermi degeneracy, I mean, that was quite a big deal. And so his calculation inspired a better calculation that was done by Chandrasekhar, and so here we get this. If you look back, we get this calculation we did. We get 1.7 solar masses, and if you assume a better model of the star, because it's not a solid sphere, it's some object in hydrostatic equilibrium, you get a little bit lower, and this is what we understand now as a critical mass for a white dwarf, below which the star collapses and you have a supernova. So you can imagine what happens. Usually, a lot of times, you have a star, you have a white dwarf, like we saw the picture of Sirius B, and it's sitting there, and it's actually sucking mass from a big star nearby. And so the mass builds up, and when the mass gets above this critical mass, the thing basically implodes and you get a supernova. And that's how supernovas occur. So there's one last piece I wanted to show you, and wait a minute. So this is the plot we had. And if you want, you can work for this. But you can actually find the radius of the white dwarf, the stable radius, and this is just a calculation that I wanted to go through. And but it's not that important. It's just some extra piece that, of course, you can find this minimum, and the expression's kind of complicated because you have to find the minimum of this equation, which you can do graphically. You can always do, but I wanted to show you could try to do it analytically, and you have to make a number of approximations and so forth. So and here's what I get basically. I get 4/5 this critical mass. Scaled mass to the minus 2/3 power by some approximations. Like I said, you can always do this graphically. So so you can actually calculate. This is just calculating going back to the because we had scaled mass, we had scaled radius, and the end of the story is that, as before, we saw that this radius goes like the mass to the minus 1/3 power, and we found that in the previous calculation. And if you want, you can check that this result we get here is the same as we found before. Actually, I haven't done that, and I was about to do that. Of course, it's going to be the same to maybe a constant. But if you want, you could actually see if it is exactly the same as the ultra-relativistic limit. What is clear is that the critical mass is the same as the non-relativistic calculation, and that's what's important. Okay, so well, that was quite a long lecture, I understand, but that was basically the story about stars, how stars die, and some of them die as just white dwarfs that get cooler and cooler until they just are sitting there. But the point is, if the mass is big enough, the white dwarf is unstable, and it's beyond this course, but that's what leads to supernovas. Okay, all right, well, that's it. This concludes our part of the course on ideal Fermi gas, and for the next lectures, we'll move now from fermions to bosons. Okay, see you next time.